Okay, let's get started. This is our 9 o'clock press conference. It's called Innovations for Understanding Weather and Climate. We have three speakers today, and they will speak in this order. We have Gerald J. Mace. He's professor of atmospheric sciences at the University of Utah in Salt Lake City. Our second speaker is Colm Sweeney. He's research scientist at NOAA Earth System Research Laboratory and the Cooperative Institute for Research in Environmental Sciences in Boulder, Colorado. And our third speaker is David Green. He's the lead for emerging science and services at NOAA National Weather Service, Office of Climate, Water and Weather Services in Silver Spring, Maryland.
All right. Well, I'd like to spend a few minutes. Spend a few minutes talking about some of the new investments that the ARM program has made in cloud and precipitation radars. Had the good fortune with the American Recovery and Reinvestment Act of being able to invest $30 million in new radars, and we are very fortunate to be able to do that. And I'd like to spend a few minutes talking about some of the motivation for this investment and show you some of the new data that seems to be coming down the line from these new radars. I'd like to start with sort of a very basic motivation for the need for this data. It's not an obvious connection between climate uncertainty and radar measurements, but hopefully I'll connect that thread here in one way or another. This is a figure from Dufresne and Bonny's paper in 2008 that really shows the source of uncertainty in climate change prediction. We all know that our ability to predict climate is not where we want it to be at this point, and that uncertainty really comes about from a number of sources. And what I'd like to illustrate here is that the majority of this uncertainty is due to clouds in these models. And if we take all of the other uncertainty combined and we compare that to the cloud uncertainty, we find that clouds are almost as much as all of the others combined contributing to the uncertainty in climate change prediction. And so the hydrologic cycle, it turns out, is one of the fundamental aspects that need to be improved in climate models, and that connects us back to these new measurements and the radars that the ARM program has invested in. Over the years, since the late 80s through the 90s into the present time, climate models have become higher and higher resolution just because of the need for better simulation of clouds and precipitation. And as they come down in resolution, as they increase in resolution to finer and finer scales, the microphysical processes, those processes that cycle water through the climate system from vapor to cloud droplets, ultimately to precipitation droplets and snowflakes, those processes are where the weak link is. And as we progress towards global cloud resolving models, probably late this decade or early next, we are going to have to parameterize those microphysical processes with a lot more fidelity than we can do now. And that's precisely why we are in need of new measurements. And I like to use this figure as an illustration. The processes are beautifully shown here that we need to be able to understand. Fundamentally, we have air motions bringing air upward in turbulent updrafts that cause condensation of cloud droplets and formation of precipitation. It's those very processes, the dynamics, the connection between the dynamics, the microphysics, and the precipitation that we have to be able to understand. And so that's fundamentally the primary goal of the ARM program, is to understand, is to build an improved understanding of those processes. And that's where these fancy new radars come in. As I said, there was a $30 million investment in new radar technology by the ARM program. And most of those radars are deployed as we speak. And I've just showing you here a map of where these radars are now located at this very moment, from the Southern Great Plains in Oklahoma to new assets up in the North Slope. northernmost precipitation radar on the planet is now collecting data on the North Slope along with several other radars. There are radars operating right now on Manus Island, east of Papua New Guinea, Darwin, Australia, and in the Maldive Islands as part of a major campaign. It's been a real experience for the radar technologists in the ARM program to make all this happen, and I see people shaking their heads. Yes, it's been a real experience doing this on the short time scale that's been necessary for the stimulus funding. So I'd like to take my remaining time and just show you some examples of this data. This is some measurements that were collected actually at Steamboat Springs last winter. We deployed the second mobile facility to Steamboat Springs, and this little thing here on top of this sea container is a W-band radar. It's a cloud radar pointing vertically. And here we have a vertical profile from the surface to about 1.2 or 3 kilometers above the atmosphere. And this connection between dynamics, clouds, and precipitation is nicely illustrated here. What you see, these colors represent the amount of power that's been backscattered to the radar receiver. The location here and velocity sort of represents the size of the particles, and this the feature you see right here is the actual cloud itself. So we see a combination of clouds and precipitation, and when I animate it, you'll see the effects of dynamics. So you see the cloud changing, you see pulses of snow falling out of the bottom of the clouds down to the surface, and you see plenty of turbulence up here near cloud top. And this is precisely what we need to be able to measure to understand the processes that process water through the climate system. And so that's the motivation for doing this and some of the early data. This, I have a number of other animations provided by Scott Collis of the precipitation radars. The types of radars that have been deployed are really a combination of very high frequency radars that measure clouds and lower frequency radars, more traditional frequencies that measure precipitation. I just showed you an example of a cloud radar. These are some examples of precipitation radars, and we're basically going to fly through a snow system, a snowing weather system on the North Slope of Alaska. This is as I said, this is the most northernmost precipitation radar on the planet, and is allowing us to observe processes in the Arctic that up to now have never been observed. There it goes. So you're flying through a snowing system on the North Slope, and it's, to a scientist, that's excitement. This. Similarly, on Manus Island, we have tropical thunderstorms. This is actually east of Papua New Guinea, and you can see we're flying into a deep precipitating system that's raining very, very heavily, and again, excitement for scientists. Now, this is probably a little bit more exciting generally because we're flying into a supercell thunderstorm on the southern Great Plains. And you can see this beast of a system right here that is raining heavily, perhaps maybe even generating severe weather. But this is what these new radars, up until a year ago, we could not do this. Now we can look inside of these processes. We can look inside of the thunderstorms. We can look inside of the clouds, and tease out the actual air motions and turbulence that are driving the processes that we need to understand. So it's just these two bullets just summarize some of those points, but I'd like to leave you with this point. I think this is very important. There's not a direct pipe between radars and climate models. There's not a wire that you attach to the back of a radar and plug it into a climate model, and suddenly all that data improves climate models. It's very important to realize that it's going to take a very large team of scientists and an army of graduate students to actually convert those measurements into understanding. We have to understand those processes, and only through understanding can we develop the improvements to climate change predictions that we need. So the radars are necessary but not sufficient, and now the fun part starts. We get to analyze some of that data and understand what the atmosphere is doing. Thank you very much. Questions are at the end. You're up.
Good morning. My name is Colm Sweeney, and let's see, is there a... Today I'm going to talk about an invention called the Air Core, which Peter Tons, who's sitting in the back of the room here, thought of about 5 years ago, and he can tell you the story of how he thought about, how he conceived of this. Today, what I'm, as the person who runs the NOAA aircraft group for the carbon cycle, my objective is to develop an observing system that's for CO2 and for methane and for most greenhouse gases from the surface up to the stratosphere. And in doing that, we deploy small aircraft as well as other larger aircraft. But what I'm going to show you today is a huge step in being able to observe the greenhouse gas distributions throughout the atmosphere, and to do it in a way that's similar to the way weather balloons are launched, and have added tremendously to both modeling of weather prediction, but also looking at how these using satellites to also improve weather prediction. So it's the observations, the direct observations that can be compared against satellites that's important here. So to move along quickly, the Air Core, which I brought a sample. This is a sample Air Core that we fly, so it's a relatively simple system. What it is a long tube. In this case, we have about 50 meters or 150 feet of tubing, and when we fly it, one end is open, and then the other end is closed. And when it goes up, we start with a fill gas here, and when it goes up into the air, that fill gas goes out into the atmosphere. We just let it passively go out. As the balloon moves up into the atmosphere, the pressure gets lower, and so the air naturally comes out of the tube. And as it goes back down to the ground, the surrounding air then gets pulled back into the tube, and we have a sample of the atmosphere. And the one thing that we can then push that sample back into an analyzer and analyze whatever gas you have an analyzer for. In this case, we've focused mostly on CO2 and methane, but you can envision this being useful for sampling any kind of gas in the stratosphere if you can develop the instrumentation to do so. The big problem that we face is that when you pull gas into a tube, it wants to diffuse in space, and so you get a smearing of your signal. And so what you do to counteract that is you have a very long tube. As I said, the tube behind me is 150 feet. We also fly a tube that's 500 feet, and we can get much better resolution when we do that. This is an example of a flight where we took, in a small aircraft, we took, the red represents an instrument that's measuring the CO2, the methane here, and the CO2 on the right, and looking at the red is the actual variability that we observe with an instrument that's on the plane. And then we also have the Air Core, which is the blue trace here, and that has been measured after we land. We simply push that sample into the same analyzer, and what you can see is that although the blue is significantly smoothed over the red, you capture all the main features of the profile. And again, you can imagine this for any kind of trace gas that you would have in the atmosphere. We've done many flights, but I just wanted to show you, this is a flight where we actually flew 3 different air cores all at the same time. So this is a small package that I have here today, and then there's several other packages. This is a typical balloon. It's a weather balloon. We also have relative humidity and temperature, so we can connect these with the weather measurements that are made on a daily basis. And so this is the launch. You can see the whole tether is about 150 feet long. And the package is at the bottom here. There's a parachute here, which is going to be used. Once this balloon pops, it just comes back down to the Earth. And this is sort of the trajectory. So we started here in eastern Colorado. One of the balloons made it up to 100,000 feet. They all landed within about 5 kilometers of each other. And these are the profiles that we get. Again, you can see one profile in green, which is the longest air core, the least amount of smearing that's happened because it's a longer air core. And then the blue, which is our miniature air core that I have here today. And you can see that while we miss some of the features with this shorter air core, we capture the major features of the profile. And it's important to note that we're sampling 99% by going to 100,000 feet, which is, I came in a plane from Denver and we went to 40,000 feet. We are sampling 99% of the mass of the atmosphere by going to 100,000 feet. So it's a significant fraction of the atmosphere that any satellite might be looking through. Why the air core? There's a couple of benefits. Obviously, the cost, because it's so simple, is the cost is mainly in getting people out into the field and deploying it. It costs about $1,000 in materials, but the actual deployment cost might be $4K. And this is compared to other aircraft that we might envision. Small aircraft like the Cessna that I showed earlier, cost in the neighborhood of $1,500. But the errors that we would get in sort of validating this against the total column are very large in relative terms. So you don't need, the units don't matter too much, but the point is that the air core allows us a very accurate column measurement versus what we might get from a small aircraft or even a jet, which could fly to 12 kilometers, which is 40,000 feet. So right now, our main emphasis is evaluating satellite measurements. We're also have developed what we call an actively pumping air core, which is just basically it's a tape recorder of the atmosphere, and so you slowly pump air through this same air core. But you put it on a UAV, and this again can be used for greenhouse gases. But I would submit that it also for any kind of trace gases that you might be interested in looking at and surveying on a near ground or in places that are hard to get to. And then so the main thing with the air core is it allows us to have accuracy and to connect our measurements directly to all the ground measurements that are well calibrated. And it is simple and cost effective. So it's one of these things that all of a sudden on a yearly basis, 75,000 weather balloons are launched. It wasn't until they made disposable systems that could actually make these observations that they were able to get and make this cheap enough to actually be able to have that network. And the air core is something that will allow us to do that from the trace gas point of view. So.
Oh,
Are you, you're on the...
on the desktop. So
Yeah.
I'll get it. Yeah. Okay, thank you. Okay. Good morning. I'm David Green from the National Weather Service. The technical expert on this couldn't make it, Mike Gerber. I'll give you contact information for him near the end. We also have representatives here from Public Affairs and Communications who can provide additional information. But I brought along my prop, and I suspect you guys all have the same type of prop, and I suspect about 99 to 100% of the people outside have something similar. And so what we're talking about is the fact that while we can collect Earth observations from all over, and there's lots of new and innovative technologies, they're all moving forward, new and innovative models. We're also finding new ways to communicate, new ways to observe using mobile devices, and responding to the social changes that make mobile devices part of our human nature. So today I want to talk about, the next few minutes, enhancing our public safety through geo-targeted alerts. Now, the aspect of public safety we're talking about is to enhance the number of varieties and ways that we have of getting important and critical information to people in a timely manner, but more importantly, the fact that we now have mobile communications, we can also look at using wireless emergency alerts where and when hazards are, where and when people are that are going to be affected. So the alerts we're talking about now are location specific, taking advantage of cell towers that are around the country, around the world, and the fact that almost everyone has something like this on their hip or in their pocket or on their hands while they're traveling and while they're moving around. Now, over the next year, we're going to see these types of messages become available. That's the news story. We've never been able to provide this type of information this directly to people where they are as they're moving around. 3 types of messages are going to be coming along. The most critical, high-level messages coming from the presidential level. Those typically you would expect, and you do get today from the Weather Service, from USGS, from other agencies dealing with imminent threats, life and property threatening, hazardous, and potentially destructive information. And Amber Alerts, important to communities, children, and other levels of awareness. Now, from the Weather Service's perspective, we have always been the ones most responsible for, but not the only ones responsible for, getting the message out on warnings and alerts. And in this case, our partnerships with FEMA, the Emergency Management Agency, mostly responsible for the crisis management, the on-site response recovery, as well as other agencies, have to partner together, along with the private sector, along with academics and the numbers, to get the information from the Weather Service, that you see on the right, in partnership with FEMA, our information, now using, and I'll mention it in the next slide, common and standard ways of collecting, assimilating, and managing that type of data in what we call the Common Alerting Protocol. And using that method, we can now distribute this information simultaneously through many, many different means to get the information to people. The one we're focusing on right now is that one in the middle there, which looks to getting that information to your cell phone. And so we're getting these weather, disaster, and other emergency information into your hand, and simultaneously, without interference effects, getting it to all these other mechanisms. Now, the Common Alerting Protocol has been around for a while. We use it domestically here. We advocate it globally. The key thing about it is that we're not even using all of the possibilities that it does allow us. But now, coming in the next year, we're going to be taking advantage of some of the features to provide better communications. And in fact, our goal is not only to communicate a warning, an alert, and a message, but to give greater insight on what that impact is and to help guide the best possible type of actions that people can take. Now, the CAP protocol is non-proprietary, digital, it's GIS friendly, so it has spatially inherent capabilities to it. It also allows, because it's a standard, a way of many people collaborating. And as I said, because of some additional features that it has and the types of partnerships we're putting together, we expect to see enhanced messaging. The little picture on the right shows 2 people sitting in front of a fireplace on a nice snowy day, while simultaneously, a few blocks away on the highway, we've got cars and trucks facing hazardous road conditions. Right now, we put out information broadly to all those people saying there's winter weather. What we need to do is get information as people drive along that maybe it's a nice snowy day, you can go for a walk or go tobogganing, but for people who are in a road condition where potentially there's hazards, they need to know the type of conditions that impacts them. And some of the things we've also learned is the type of information that we want to put out is very difficult to put out right now. Because when we tell people there's maybe a few inches of snow, for some people it's a lovely, beautiful afternoon. But those few inches of snow on the roadway in the right place can be a disaster for a truck, an airplane, or some other condition. But the geospatial, the geotechnical aspects of what we're trying to do, I think is going to be very important. So let's just mention that this is collaborative. This is public and private. Many people have a role in making this happen. The distribution of this type of capability through our cell phones is voluntary. It's voluntary on two sides. It's voluntary on the side of the providers, your wireless providers. It's also going to be voluntary on those who receive it. So it'll be free and open like our information is now from the Weather Service and from other disaster agencies who have that mission. But the way it's used and distributed will be voluntary and will meet certain standards which will allow additional collaboration. Now, it's moving out in 2012. The key to when you particularly will get it and everyone else will get it on their cell phones is going to be up to your particular provider of wireless carriers. There's a lot of test and development going on in certain sites around the country right now. The dates and locations for specific rollouts, again, customers will be informed by their providers when they can expect it in their area and how to activate their systems and their phones to get these services. So let me just wrap up here. So the geo-targeting of new mobile media will put alerts in your hands. And if you're driving, I'll say hands-free devices. And it will provide that information where the hazard potential is, and as you move around, that information will become available to you. It's absolutely public-private capability and responsibility and a collaborative way of making this information available and received. The Common Alerting Protocol contributes to what we'd like to call not just alerting but decision support. And furthermore, this is a great example where science, service, and collaboration, just like what you heard about the observing systems collecting information, this is the type of example where those science services and technology are coming together to promote safety, security, and the economic opportunities that these merged capabilities will provide. If you have further questions, I mentioned Mike Gerber, a technical lead on this. There's Mike's contact information. I'm the lead on emerging services in science, which range from things like the science dissemination you're hearing about today. Later on today, I'm talking about renewable energy, and tomorrow I'm talking about forecasting jellyfish. So we have a lot of emerging services. And Katie Human is here in the audience from NOAA Communications if you have some questions for her. Thank you.
Thank you, speakers. We're ready for questions. Any questions here from the floor?
Hi, Liz Gallagher from Environmental Research Web. I have a question for Jay. On what kind of timescale do you hope to bring in the improvements from your radar?
In the climate models? That's a really difficult question to answer. It depends on a number of things. Depends on the radars continuing to work as they have been working. It depends on the funding that's available to fund the students and the scientists to do that analysis. Both of those are, especially the latter, is fairly uncertain at this point. Assuming the best of all possible situations, I would say, conservatively in the 5 to 10 year time frame. It would for us to fully utilize the information and develop the understanding, develop new models, validate those models, then fix what we didn't do right. And it's an iterative process. And I would say within the 5 to 10 year time frame, we could expect improved climate models.
Do we have any other questions? Any questions from the chat? Okay, I just also wanted to mention there's some handouts at the back about the ARM climate research and the radar. So thank you very much for coming and speaking, and thanks everyone for being here. Our next press conference will be at 10 a.m. That's Small Climate Changes, Big Ecological Impacts.